In our last screencast, we looked at the nucleus part of atoms. Now we're going to look at electrons. Before we do, I just want to bring up the study guide and just kind of highlight how hopefully you've seen the relationships, right? So we started by looking at atoms. We looked at the nucleus as a subset of that, protons and neutrons. And you can kind of see like, wow, yeah, we're really following that outline. So again, can't emphasize it enough. This outline is really useful when you're taking those notes. So use it. Not sure if I pointed this out, but there's also page numbers on here that correlate to where you can read about these things in your textbook. And we kind of leave it up to you guys to decide when do I want to do the reading. Some students find it's helpful to read before hearing a screencast or lecture, and so they can do so. And other students find, I think more students probably find that this is more helpful, is to hear about it in class, watch the screencast, whichever it may be, and then go back later and read the book where you can kind of go back through your own pace. And, I would encourage you to have your notes out while reading the book so you can kind of follow the notes as you read. And then if there's something that wasn't very clear in the notes, you can kind of zoom in on that text and try and make sense of it, adding to your notes as necessary to make sense of it. But I definitely would encourage you to do that assigned reading. I promise you it will be helpful and really enhance your understanding. So, electrons. The electrons have the negative charge here, and they're often seen kind of traveling around the nucleus like this in these little circular rings. Well, these circular rings are called energy levels, and they sort of represent the energy of an electron. And the amount of energy is based on the distance from the nucleus. You kind of think of the nucleus having this positive charge because of the protons. The electrons have a negative charge, and so there's like some potential energy there because the electron is the negatively charged electron is separated from the positively charged proton. So this has a little bit less energy than this. This has more potential energy because you're pulling those two things further apart. Just like if you have a ball higher off the ground, it has more potential energy because the negative wants to attract the positive. So you might wonder, well, why doesn't it then go and attract to the positive and go smacking into the nucleus? Well, the reason why is that these electrons are actually limited to these locations, which are called orbitals. And that is a little beyond what we need to do in AP Bio, but a good analogy would be like a flight of stairs. If you wanted to put your foot, or an electron, on a flight of stairs, you can put it here or here. You can't put it in between. You cannot put your foot on a step in between because there's no step there. So the electron is kind of like that. It can be in this energy level or this one. There is no in between. It's there or there. That's it. It's called a quantum leap to go from one to the other. So it's kind of stuck here or here. It can't just go drifting down to the nucleus. Anyway, something you may remember from chemistry, we call it the pretty colors lab. You may remember burning salts. You dip them in a Q-tip and you put them in flame, and then the flame glows a pretty color. And whether or not you remember that, it's kind of a cool phenomenon. And what's actually happening there is this phenomenon. Sometimes electrons can absorb energy and move to a higher energy level. And here you see this happening. Here's an electron that was in this first energy level. It absorbs energy, woohoo, jumps to this higher energy level. And then sometimes it can give off energy as it drops back down to a lower energy. So here, as it drops back down, it's going to give off energy. And so basically, these different salts that are being burned, the difference in energy between these different energy levels varies. And the amount of energy given off correlates to different wavelengths of light, which have different energy. So, basically, when you put these salts in the flame, woohoo, the energy of the flame allows the electrons to jump to a higher energy level. And then those electrons drop back down and they give off a very specific wavelength of light, which correlates to these different colors. This actually becomes very important when we talk about photosynthesis, the idea that electrons can jump to a higher energy level and then drop back down to a lower one. So foreshadowing. Okay, so let's talk about these energy levels here. You can actually use the periodic table to kind of draw out the number of electrons in each energy level. So if we were to represent carbon with what's called the Bohr model of the atom here, you put the nucleus in the middle, 6 protons, 6 neutrons, and then each position of the periodic table correlates to one electron. So the first energy level, we call it n equals 1, is this first horizontal row across the periodic table. And there's two elements here, which means this first energy level, this first circle, has two electrons, 1, 2. Then, since we're going to a second horizontal row on the periodic table, we have to draw another energy level in this ring. And this has 1, 2, 3, 4 electrons till we get to carbon. So we put them in 1, 2, 3, 4. And so that's how you draw it. So here we have carbon with its 6 protons and then 6 electrons. And since the positives balance out the negatives, it is neutral. There is no charge on carbon. Now it turns out that, yes, we can represent the atom this way, but it's a royal pain. I don't want to have to write 6 protons and 6 neutrons and and draw all these circles. There's just a lot there, and we shouldn't have to, right? If it's carbon, we know it has 6 protons, and we know that most of the atoms at least have 6 neutrons. So is there a better way? Yes. And the better way takes advantage of the fact that really the only electrons that are kind of chemically interesting to us are the ones in the outermost energy level, i.e. the valence electrons. So valence electrons are the electrons in the outermost energy levels, and these are the ones involved in chemical bonds. So if carbon is right here, it's in the second horizontal row of the periodic table, that means the second row is our outermost energy level. So to represent this in a simpler way, it's called a Lewis dot structure. We would simply write the name of our atom, carbon, whoosh, there it is. And then in the second row, starting there, 1, 2, 3, 4, we draw in 4 dots because there's 4 positions here. So 1, 2, 3, 4. And the rule is you always keep them in opposite quadrants, so kind of north, south, east, west kind of thing. You don't double up until you have to. If we were to continue on and needed to add more electrons, then we can start doubling up. But you don't double up unless you have to. Electrons tend to be antisocial. So, so to kind of tie this together, since electrons are involved in chemical bonds, and since the number of electrons is equal to the number of protons, ultimately protons do determine the behavior of an element. So this is why carbon behaves differently from nitrogen. Carbon has a different number of protons and therefore a different number of electrons in its outermost energy level, and therefore behaves differently at a chemical level. So let's practice a little bit. Take a moment to represent Lewis dot structures for oxygen, nitrogen, and hydrogen. I really encourage you, pause the video, try this out. I'm about to reveal the answers. Are you ready? Oh, parts of the slide didn't load. Well, I'll be darned. Okay, let me pause this 1 second. Hey, we're back after what was our first of what I'm sure will be many technological glitches this semester. Anyway, here are the answers. So, we'll do hydrogen first. It's just right there. Outermost energy level is the first one. So there's one element here, hydrogen. So it gets 1 dot. Boom, there it is. If we go to nitrogen, it's in the second energy level. So we go 1, 2, 3, 4, 5 dots. And we start 1, 2, 3, 4, and then the fifth has to double up. Boom. Oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. And so again, we go north, south, east, west. 1, 2, 3, 4. And then we have to double up for 5 and 6. Now again, with oxygen and nitrogen, we know that there are 2 electrons in that inner energy level, right? So just like carbon, there's 2 electrons there, but they're not very chemically interesting to us. So we just kind of ignore them and just highlight these valence electrons, okay? Now, it turns out that there's this rule called the octet rule. It turns out that atoms will tend to share, donate, or accept electrons in order to fill their outermost energy level. So for carbon, nitrogen, oxygen, the outermost energy level is represented by this position on the periodic table because that would be a full outermost energy level. For hydrogen, it would be this one. Because helium represents the position of the outermost energy level. So it's called the octet rule because for most of these horizontal rows, that's 1, 2, 3, 4, 5, 6, 7, 8. We kind of ignore these middle ones because they do weird things that we won't worry about. So if you ignore those middle ones, kind of these 2 plus these 6 add up to 8, hence octet. So So we'll get back to that octet rule soon enough. One final little thing about electrons. There is this thing called electronegativity, which is the attraction of an element for electrons. It turns out that different atoms tend to draw electrons in a little more strongly than others. And electronegativity tends to increase as you go up and to the right on the periodic table. And the most electronegative atom in the whole wide world is fluorine. Now, the reason why this is because remember the octet rule says atoms are most stable when they're in this outermost energy level configuration. So fluorine is like one away from being stable. Have you ever played Monopoly? The goal of Monopoly is to destroy your friends, and the way to do that is to get, three properties of the same color. And if you have two properties of the same color, you're really close to destroying your friends, and you just really need that last property. That's kind of like fluorine. It's like, I'm so close to that outermost energy level. I really want that electron to fill myself out. And so chlorine, bromine, these are all very electronegative as well, but because they have a lot more of those inner energy level electrons there, that kind of reduces the electronegativity a little bit. So that's why it increases in these directions. So electronegativity is a pretty important concept soon enough as well. Okay, so at this point, I'm going to pause and wrap this up, and then in our next screencast, we will look at chemical bonding.